Hi everyone, welcome to the fourth episode of Math and Beyond and this podcast. Today we are going to talk with Shreesh Sahai. I hope I have pronounced it correctly. We are going to talk about black holes. It is quite a general topic, so we have some questions and we are going to start from some basic concept. Now I will send the invite to Shreesh. I will see you soon. Hi, Shreesh.
Hi, Francisco. How are you?
Hi, how are you?
I'm good as well.
Yeah, I'm fine. Where are you?
Great.
Where are you?
Seems to be a little bit of network issue. Your voice is breaking a little.
Sorry, can you repeat?
Yeah, I was saying your voice was breaking a little, but now it's clearer.
Yes, sorry. I said where are you located now?
Oh, I am in India, in Delhi. I am completing my master's MTech in nuclear science from Amity University in Noida, which is in the capital region.
Okay, I said I gave a small introduction before, saying that we were going to talk about black holes today. It is a general, quite a broad topic, so I made a little outline of points that we will touch upon. But so I think we can jump into it, and yeah, I would like to ask you firstly if you can explain what is firstly a black hole.
So a black hole basically is an astrophysical object which is characterized by its extremely high density. So in your first podcast that you recorded with Manvi Jain, she explained about the life cycle of a star, and where you talked about the heaviest of the stars going off in a supernova explosion. So most of the heaviest of the heavy stars, once they die off, what happens is that there is no fusion which is happening in the star. So there is nothing which is providing an outward force to balance out the gravitational attraction which is happening within the star. And slowly and steadily, the star starts to collapse because of its own mass. And in that situation, it ends up going to such an extent, or all of that mass gets confined in such a little space with such a high density that escaping from that body becomes impossible, because to a particular region around it, the escape velocity from that body is equal to the speed of light. And as we all know, that no body is allowed to travel at the speed of light. So there is no information that can escape out of a black hole. So such a physical entity is what you call a black hole.
Okay, you mentioned before the event horizon. What is briefly? So we have this picture of a black hole, which yes, we can correctly depict as a black object. What is the event horizon of this black hole? What would we see, or what does it represent of a black hole?
So the event horizon is basically the point of no return for a black hole. It is from the center of a black hole, it is that distance at which the escape velocity from the black hole is exactly equal to the speed of light. So if till the event horizon you are able to achieve enough velocity, you may be able to escape out of the black hole, theoretically speaking. But once you cross the event horizon, there is no way to return from it. So uh, I mean, once that limit is crossed, there is no means to escape out of it. You can think of the event horizon like a fencing around your home. So what it does is it protects everything which is inside the home uh, from spilling out. So the event horizon does something similar to that. It does not allow anything from which is inside the black hole to go out of the black hole. That is how we classically understand the event horizon.
Okay, And when if one reads a very simple article about black holes or looks up an image on the internet, a property of a black hole that one is very likely to encounter is the singularity. Is the singularity that we find at the center of a black hole. And related to this singularity, there is a lot of let's say controversy. There is a lot of controversial debate because it is a point that we cannot explain. Can you tell us about this about the singularity and why does it challenge our understanding and our theories of physics, so quantum mechanics and general relativity? What is wrong there? What is going on?
When we study mathematics, and especially when we talk about differential equations, uh, people in their high schools, they are taught about a singular point where the differential equation gives no solution, it gives a zero solution. Yeah. So singularity basically is a breakdown in a four-dimensional space-time. What is a space-time? Space-time is a concept that is explained by imagining that the three dimensions that we know, length, breadth, and height, get interwoven with the fourth dimension called, which we call as time. So an XY plot on which one of the axes represents the position while the other represents the time. That graphical representation is what you call a space-time. And a breakdown in the continuity of that space-time is what we call a singularity. So at this point, we expect certain physical laws to be valid. However, when we actually start to implement those laws, we start to work out that mathematics, we find out that it doesn't really obey or doesn't give the same outcome as we would expect it to do. So suppose we do a calculation here on Earth, we find a particular outcome. But when we do the same calculation at the center of a black hole, we don't get the same outcome from that. So that point is basically what we call a singularity. And the interesting thing is that there are some theories regarding the black hole which are expected to hold true. General relativity is supposed to hold true, and later we found out that quantum physics and thermodynamics, they should also govern the ways in which black holes uh, behave. Certain properties of black holes are explained uh, by these theories. However, we find that sometimes the black hole does not. If I put it like this, that at the singularity, we don't see these theories entirely work out the way that we expect them to. Uh, I think that is merely around what we do know.
Mm-hmm.
Yeah.
Okay. Okay. Yeah, I find it a challenging concept. The concept of a black hole singularity, because they try to explain how and in an infinitesimal point, let's say everything is infinitely dense. We have infinite density, and time gets stretched infinitely. So we have infinite time dilation. And if I think about it, sometimes it's challenging indeed to grasp as a concept, because I think, okay, let's think about my physical reality, so what I see and experience on a daily basis, where time flows regularly, and I have a certain defined and finite gravity attraction towards Earth, so there is a certain density. And now I think, okay, now imagine there are points as you said, in the space-time, where we have as properties, as physical properties, we have infinite density and infinite time. And I wonder, how must these places be? How much different they must be from our physical reality? And that's where I get very excited about thinking this mind-boggling concept, which is sometimes
it's actually very interesting area of research as well, because uh, everything that you think is common understanding, which you can work out over here, you don't find those things working out very well. For example, one of the biggest challenges that we face in today's physics is that we can't basically find a common theory for general relativity as well as the quantum theory, right? Uh, However, we see that for black holes, both of these theories play certain roles. So general relativity actually predicts how black holes should be forming, but quantum physics also explains about certain emissions around the black holes. Somehow, both of these ideas are valid over there, which exists between the singularity and the event horizon. Uh, but that's not something that we've been able to figure out at the moment. So that's what makes it a very interesting area of research.
Yeah, so, yeah, because we do expect at least we do hope that ultimately what is let's say what is the candidate, either string theory or the theory of quantum gravity. We hope that it can explain really what happened in the domain of the large, but in a point which is infinitesimally small, so at the singularity. So where we combine general relativity and quantum mechanics together. That hopefully hopefully we will assist to these discoveries within our lifetime. But I am not sure about that. So we just have to open and maybe contribute to that. We never know.
Definitely.
So I would like to ask you, what are some we described a black hole per se. We described the event horizon, and within we go inside the black hole, we find a singularity. But are there any phenomena, let's say astrophysical phenomena, related to black holes, such as like I hear in articles they talk about accretion disk, okay, or jets. What are these terms?
So, in astronomy, the term accretion, it means an increase in the mass of a celestial object like stars, like black holes, etc., due to some gravitational interaction or gravitational attraction. So, if a body is pulling another body onto it and sort of combining with it gravitationally, and that is causing an increase in its mass, that process is what we call an accretion process. So when a black hole, which is known as the accretor, is pulling stuff towards it, that stuff such as particles, gases, dust, plasma, etc., uh, it follows a spiral path as it loses its energy and its angular momentum. So, and what we usually think is that if this is a black hole, particles would fall straight into it. But that's hardly the case, because a lot of the particles that we see have some amount of angular momentum which is associated with them, right? As it is falling inside the black hole, instead of falling directly, what it does is it spirals around the black hole and eventually falls into it. So it the path that is being followed by these particles, it is a very thin disc-like spiral that it follows to fall into the black hole, and that is primarily due to the conservation of angular momentum, uh, which we know is conserved for any rotationally independent or undisturbed system. So as the particle tends to get closer and closer to the black hole, it starts to move faster and faster. And uh, when a lot of these particles they start to spiral around the black hole, we get a structure which looks like a disk, and that disk-like structure is what we call an accretion disk. So, if you may have seen some, ice skaters, when they in their performance, they sometimes tend to hold hands and pull closer. So you see them go spin a little faster, and if they push themselves further apart, they tend to move comparatively slower. They spin a little slow. So that is primarily because of angular momentum conservation. And that sort of a phenomena is what we see on the accretion disk. Now, when these charges, these charged particles, are moving all around the black hole, we find that moving charges, they produce electric and magnetic fields, right? And we know that when a particle is moving at an angle in a magnetic field, it experiences a force called the Lorentz force, which provides some change in its trajectory. It provides a change in its mass. In fact, you find that Lorentz force is such an integral part of any charged particle interaction that every single particle accelerator that you see working on Earth, all of them in some way or the other utilize Lorentz force to accelerate these particles. So when a particle is moving at an angle in this around this accretion disk, it experiences a force which either pushes it upwards or downwards along the rotational axis of the accretion disk. And these particles, they tend to gain a lot of velocity and become highly energized particles, and they shoot off from along the rotation axis. And that is basically what we call the jets that are emitted from the black hole. So jets are very highly energetic particles which basically spew out along the rotation axis, and sometimes they may be so highly energized that the black holes, which are usually around the nucleus of a galaxy, these particles sometimes move so fast that they leave the galaxy itself. And when more and more of these particles leave the galaxy, it also hinders with the formation of different stars within the galaxy. And suppose some of these particles, a small fraction of them, if they are directed towards Earth, we can study them to get an idea of the environment around the black hole. So there's an experiment at the GSI facility called NewStar, that aims a little bit to understand these particles, specifically by studying the X-ray emissions. And that is basically what you call as the jets. So you might have seen the images in which from black hole you see these white sort of conical structures coming out from the top and the bottom, and there's a little disc-like shape around the black hole. That's the jets and the accretion disk, respectively.
Okay. That's very interesting. Fortunately, we can find we do have some proof, some effects that we can measure of these black holes, because otherwise we wouldn't we wouldn't see them. So yeah, okay. But I once read a book about of Stephen Hawking, where he was explaining some theories about black holes and giving some explanation. And he said a very, let's say challenging thing to think about. He said that black holes can evaporate through the so-called Hawking radiation. But I I wonder, what does it mean? What do we mean when we say that black holes can evaporate? Because usually, if I think about a star, a galaxy, or any object, I say, okay, can a star evaporate, or can a planet evaporate? What does it mean conceptually, physically also?
So before I get to that, I think I should give a little bit of a history on how the entire concept of black holes came into being. Right. So we often attribute Albert Einstein to be the guy who found out or who proposed the idea of black holes. But much before Einstein, somewhere in the 1700s, there was an English physicist called John Michael, and he talked about bodies, which would hypothetically exist in this space, which he proposed would have the same density as the sun, but they would be so heavy that escaping from these bodies would be an impossibly difficult task. And that was the first idea of something like a black hole which was proposed. Eventually, of course, by 1915, Albert Einstein gave his theory of general relativity, in which he described certain equations for the four-dimensional space-time. And when one of these equations was solved by a man called Karl Schwarzschild, he proposed a body that would that if you compress enough matter into a particular region in within a particular radius, which we call the Schwarzschild radius, uh, it would be impossible to escape from it. And that was the first idea of a black hole. And till this point, nobody disagreed that once something enters a black hole, it is impossible to escape from it. And that, I think, is one of the biggest uh, presumptions that people have with black holes, or one of the most tightly held ideas about a black hole, that once something goes inside, there is no way for it to come out. And that is true as long as you consider the classical picture. But we also know that around the 1900s, early 1900s, a very revolutionary theory came into the field of physics called the quantum theory, right? And uh, almost 60 years till after Einstein had proposed his equations of general relativity, nobody questioned the idea that black holes could also have some quantum effects. Because, of course, we don't expect heavy objects and large scale objects to go in accordance with the laws of quantum physics. For example, the laws of quantum physics are immeasurably small when we consider ourselves on our macroscopic world. So we don't see uncertainty in the position and velocity when we are moving or when you're driving a car. So nobody gave uh, that any second thought till the time in 1975, Stephen Hawking came up with a paper called Particle Creation by Black Holes. And this is when he was in at the Cambridge University. And there he described this idea that black holes may not be as black as we consider them to be. Now, why did we call them black? Initially, it was assumed that since black holes don't emit anything, there is no radiation which is coming out of them. If there is no radiation which is coming out of them, there is no signature that we get. We are unable to see what a black hole is doing. And that's why, due to the absence of any EM radiations, we call it a black hole. But Hawking argued that black holes may not be as non-emitting as we assume, and they should in fact emit some sort of thermal radiations. And in this paper, he gave a lot of equations and a lot of calculations and diagrams in which he explained how these emissions would happen. But I best understand them with the analogy of this concept called the dynamic Casimir effect, right? So, uh, in the field of particle physics, we describe something called the virtual particles, which are formed in empty space. So, the idea is that you borrow some energy from the universe, you create a particle and its antiparticle in free space. And these particle and antiparticle pair, they annihilate to give the same energy back to the universe. That's uh, that's an idea that you would also find somewhere within Feynman diagrams when you find internal loops and everything.
Okay,
So
and so basically this is what we call a virtual particle. So a pair of a particle and an antiparticle, right?
right.
Yeah. How do these but how do these virtual particle occur in the universe? How do they arise?
Okay. So the idea is that what we call an empty space, it is not actually empty, but since it is possible to create a pair of particles as long as they annihilate and give uh, some energy. Okay, so to create particles out of nothing, you would require some amount of energy, right? We know the famous equation E equals mc squared. So to create mass out of nothing, you would need some amount of energy to get converted into mass. And usually when that happens, it is in a pair. So if you have a particle, if you have an electron, you would always have an anti-electron or a positron, which is produced with the electron. And since it is being formed out of nothing, uh, the argument goes as that some energy was borrowed from the vacuum of the universe to create these particles. And shortly after their creation, they annihilate and give the energy back to the universe. So it is like saying you took some loan from somebody, you did your work, And once you have done that, you return, you repay your debt to the lender. It is a concept rather similar to that, right? Does that make some sense?
Yeah, yeah, yes, okay.
So the idea is that suppose these particle and antiparticle pairs are created, and somehow I give them some energy or some force that pulls them apart from each other, and I don't let them undergo annihilation. Then these virtual particles which were created, they actually turn into real particles because I created particles out of nothing. Now, we just discussed that if we are borrowing energy from the universe, we need to return it back. Yeah, because energy can neither be created nor destroyed. So, how do I account for that? So, the amount of energy that I put in to pull these particles apart from each other or take them away from each other, that energy must be equivalent so that it energy must be equivalent enough for to be equal to the mass of these particles. So suppose I have an electron and an anti-electron pair, and I pull them apart. Electron has a mass energy of 511 keV. So twice of that is 1022 keVs, right? So if I give them enough energy and I pull them apart, in some sense, I'm compensating for that energy and therefore creating real particles out of nothingness. Does that
Okay.
still make sense?
Okay.
Yeah.
So basically, what you're saying is that within, no, sorry, close to black holes, we have what are the quantum fluctuation, and so virtual particle gets created. So we have a particle and an antiparticle. But when we are close to a black hole, it can happen that one of the two falls into the black hole, and the other
Exactly.
runs away. Okay, if
Exactly.
one falls into the black hole, we have no trace of it. But the other has now no companion. Okay, if the particle
Right.
falls outside, escape the black hole, then it has no antiparticle to annihilate with.
Right.
And so this particle must be created from somewhere. And what you're saying is that that is what we intend, what we mean with black hole radiation. This pair of particles which can
Right.
escape the black hole pool. Okay.
Exactly. So again, for those particles to be separated enough, that energy comes from the energy of the black hole itself. So in some sense, it can be understood as if the black hole is throwing out a particle from within itself. So net effect, net energy effect difference is equivalent to if a black hole was hypothetically supposed to shoot out a particle from within itself, we would get the same result, same effect as that.
Okay. Okay.
That
And so,
particle, that radiation is what we term as Hawking radiation.
okay. Okay. And then how does it work? Why this radiation makes a black hole evaporates over time? And also how does it take? How much does it take? Can they evaporate overnight?
Okay, so there are certain equations which govern how fast a black hole would evaporate. And it just so happens that the heavier that a black hole is, the slower it evaporates, which means that suppose there's a black hole which is of many times the mass of the sun. Yeah, it would evaporate much slower than a black hole which is of a much lighter mass, right? So, and that is primarily because the rate of emission is the emissions are happening. What we are getting out are basically thermal emissions, right? So, thermal emissions are a function of the temperature of a black hole, of a temperature of the emitting body, and the temperature of a black hole is inversely proportional to its mass. So the heaviest of the black holes tend to emit very at a very slow rate, whereas the lightest of the black holes, which have the highest of the temperatures, tend to emit at a very fast rate. So most of the heavy black holes that we see, that we read about, they won't completely die off within our lifetime. They would take much longer to emit. But if there are some black holes which are very light, which are very small, they can evaporate at a much faster rate.
Okay, and when we say that a black hole can evaporate, we literally mean that the black hole in itself and everything that has fallen into it, what happens? It disappears. Like literally, it cancels itself from the universe.
Exactly, it just cancels itself from the universe. So
and we have no trace of
everything
it.
that, sorry?
And we have no trace of it. Or do we?
And we have no trace. We would never be able to figure out that there was a black hole at this point once upon a time, because it has emitted everything that was there inside and it does not exist anymore.
Okay, but then, wait a second, but then if I throw something into a black hole, okay, I know it is, it must be there, but if if a black hole disappears, okay, and everything that has fallen inside has disappeared, then where this information has gone? Because if we are reasoning logically from this point of view, then one may say, yes, information that has fallen into a black hole must disappear. But this basically goes against the second law of thermodynamics, which says that information can never be lost. There is the conservation of information. Then how do we how does this work? How can we preserve information, or does information actually get lost inside a black hole?
That is actually a very valid argument, and that is something that has troubled a lot of physicists for a very long time. Most significantly of them, it was Leonard Susskind, who had an issue with the idea of black hole evaporations. So, as you mentioned, according to thermodynamics, information about a system can never truly be lost, right? But when you talk about,
I'm sorry, okay, I interrupted quickly. What do you mean with information? When I say information, what do I mean about an object?
okay, so suppose if I was to describe information in our context, if suppose when I look at you, I know that you know what, you wear specs, you have a particular height, you have a particular hair color, and everything. There is a particular genetic code that is there for you, and so on. So if I were to note down all of these things specifically and somehow recreate all of them, assemble them into a human being, I would be essentially recreating a version of you, right? With the same genetic code, with the same height, with the same hair color, with the same stylish
Okay,
spectacles.
so basically the information is meant as the, let's say, physical properties of a whatsoever
Exactly.
object.
Exactly.
Okay.
So when I talk about that in terms of fundamental particles, let's say electrons, we talk about the mass of the electron, the charge of the electron, the spin of the electron, uh, sometimes even what is the velocity, the position, all of those physical attributes, physical properties, they are what we term as information.
Okay,
Of any particle.
But then, wait a second. If information is, let's say, can never be lost, as the second law of thermodynamics says. But if I have now I take a plate, I let it fall in the ground and it breaks, then it is not anymore a plate. So the information contained in a solid plate must be lost. How can information be conserved if a plate falls and breaks down?
When a plate falls and breaks down, of course, it is no longer a usable plate the way that we intend for it to be used. But every single particle which is there inside the plate still has its own properties. If you could assemble it in a manner, then you would be able to recreate that plate if it was possible for us. Now, when the plate breaks down, it shatters, the plate is not usable for us, or we cannot interpret that those shattered pieces as useful as a useful plate. But that does not mean that those pieces do not resemble the plate itself, right? So in case a particle is in case I usually take the example of Lego blocks. So we know that Lego makes these toy cars and everything, right? Suppose I was to take one of those cars and I was to smash that with my feet, right? Now, if I don't have the manual, I would never be able to recreate those pieces into a car. But I know that as long as those pieces exist, it is theoretically possible to reconstruct that car. It is just that it is not possible for me to do that because I am unable to interpret how to join those particles together, how to fit them in a particular manner that it looks like a Lego car again, right? Same goes with the plate analogy. So the fact that I am unable to interpret a particular thing as a particular information is a separate idea. But to say that that information itself is lost from the universe, that's a different claim altogether. It is just that the information is out there. I'm not able to understand it. I'm not able to use it in any sense. Uh, that, of course, is the limitation that we do face, but that does not mean the information is not there at all.
Okay. Okay. So basically, when we yeah, let's say an analogy in our physical universe, information to be lost would mean that something with its particles component and its physical properties would literally disappear from the universe, would cancel itself, and we wouldn't be able to trace it anymore. We wouldn't be able to trace its existence, its physical properties. That's what we mean with the loss of information.
Right. So a loss of information would mean that it doesn't exist. There is no way to find out about that uh, in any of its forms. So in its particle form, in its energy form, there is no way to know that this entity existed at a particular time. And that's what physics says. It's not possible. It's not possible that something to be lost in a way that we can never trace it out, given, of course, the time and the effort and all of that to find out about them.
Okay, but then how is it possible that Stephen Hawking said that we have an information paradox, such so that everything that goes into a black hole gets lost finally once the black hole evaporates. How can all the things, black holes are huge, right? They they eat a huge load amount of stuff during their lifetime. How can all this information get lost? Or does it really get lost?
Uh, this entire discussion regarding whether or not information is lost because of Hawking radiation, uh, it's actually termed as the black hole war. Uh, and there's a book by the same name, written by Professor Leonard Susskind, where he makes the exact argument that you are, that if a black hole is emitting Hawking radiation, which is very randomized, it has no connection with whatever is there inside the black hole, then what happens to the information? How are we losing that information? So Susskind suggested, he gave a probable solution for this, where he suggested that something like the holographic principle could be the solution for the information paradox. The holographic theory, basically what it says is that our entire universe, it can be considered as a bubble with a two-dimensional surface and a three-dimensional volume inside it. So all the information within the universe is not actually a physical three-dimensional entity which is moving inside, but it is a projection of everything that is encoded on its two-dimensional surface. And whatever we see is a mere projection of that. So if we consider the same argument for a black hole, because inside a black hole, when you consider a black hole, you can assume that the event horizon is the surface of this black hole, and there are some particles which are inside the black hole. So Susskind suggested that what if uh, there are actually no particles which are inside the black hole, but they are projections of the information which is encoded on the surface of the black hole or on the event horizon. Uh, if that is to be the case, then as we discussed about the process of Hawking radiation, uh, the radiation is formed at the event horizon, right? So when it is being formed, it is downloading the data from the event horizon and encoding that, imprinting that information onto itself, and that's when it is being emitted. So sure, black hole took in some information. It was preserved on its event horizon, and when it started emitting, it is letting off the same information in a manner which we would not be able to interpret for sure. But that information is being re-released out into the universe. And so when the black hole completely evaporates, all of the information is dispersed into all the particles that it emitted over its lifetime. And therefore, the information is not actually lost, but it is distributed and dispersed out into the universe. And this idea, this probable solution, did gain a lot of attention uh, to the extent that in around 2015 or 16, Hawking himself wrote a paper called Soft Hair on Black Holes to explore the mechanism or the possibility of this process, in which the holographic principle could act as a potential solution to the information paradox.
Okay, so basically what Susskind was suggesting with the holographic principle is that, okay, we cannot see within the black hole, but now let's assume stuff falls inside the black hole. This information, this object, so the information contained within this object gets encoded pretty much. We would think of encoding a computer, so in a sort of language, would get encoded within the in a, I would say, in a lower dimension within the black hole. And through the Hawking radiation, this information gets ejected outside in the universe, and that is how Susskind preserves, let's say, make the second law of thermodynamics to be preserved. It says the information we get within the black hole gets encoded in a lower dimension within the black hole. This information gets, let's say, gets dragged and ejected through Hawking radiation, so that the information is never lost. It is just dispersed around the universe after it has been ejected by the black hole. Is that correct?
Exactly. So Susskind, he basically said that the event horizon is not just a boundary; it is a database. So all the information about the black hole is stored onto that database, and whenever some particle is being made to eject out of a black hole, to be emitted out of a black hole, it is taking some part of that database and it is going away with that. And as step by step the entire black hole evaporates, all of the information is taken from that database, encoded onto these little particles, the Hawking radiation, and that is dispersed out throughout the universe. That's exactly. So in that manner, he proposed to preserve the laws of thermodynamics.
Okay. So hopefully this law holds, because otherwise the second law of thermodynamics is to be violated, and we wouldn't rather this outcome. But okay, can I ask you now about yeah, I've read also about primordial black holes. What is this object? Why do we refer to it with the word primordial? How do they differ from ordinary black holes?
I really like that question because my current work is associated with primordial black holes, and I'm currently dealing with how they are emitting different particles. Uh, Primordial black holes, primordial. The word primordial usually refers to something which is very old, right? Which is ancient in some sense. The idea is that these primordial black holes, they would have been formed very early in the universe, much before the formation of any stars, the formation of any complex bodies, but right around the time that matter started getting created in the universe. So different theories tend to predict certain stuff, but they say that these primordial black holes would have been formed somewhere around the first second after the Big Bang. So Big Bang happens, 1 second passes, and there are black holes in the universe. And these black holes are what they call primordial black holes. How do they differ from the normal black holes? Well, normally a black hole, as we discussed, they are formed when a star collapses at the end of its lifetime. So we know that for stars like Sun, the lifetime is around 10 billion years, right? So it would take billions and billions of years for some of the stars to eventually form a black hole. But primordial black holes, they are formed when in the early universe, because of certain reasons, uh, there are certain pockets in which the matter got very close together. It started getting denser, and without forming stars, all that matter itself compressed into a very small region and formed a black hole. So uh, instead of taking billions of years to form, it got formed within 1 second of the Big Bang. Instead of necessarily being as heavy as some stars and beyond, it can be as light as zero point zero 0.01 milligrams. And that is basically the difference between primordial black holes and what we normally understand black holes to be like.
Okay, but then, so basically, a star to become a black hole, it means that it must have a certain mass within, let's say, compressed in a certain, in a certain within a certain circumference, so that the smaller the circumference, the greater the density, until it, until it gets how do you say, until it shrinks down the Schwarzschild radius and it becomes a black hole. But then, if you said that a primordial black hole can also be very, very, very light, what is the what is the circumference, the size of these primordial black holes? They must be infinitely thin.
They would be very small. So primordial black holes can be as small as protons. They can be as small as the heavier ones can be as small as say a golf ball, and they can go up to be a little heavier than that as well. But imagine some of these smallest things that you can think of. That's how big some of these black holes can be, would have been back then, because there are certain studies, primarily by Sir Bernard Carr, who gave certain restrictions on the size of the primordial black holes which would exist today. So he said that black holes would have been very small when they were formed at 1 second after the Big Bang, but any of the primordial black holes which was less than 10 to the 15 grams would have completely evaporated by now. So any primordial black hole that we would be able to see today must have been more than 10 to the power 15 grams at the time of its creation for it to still exist till date, which means that there must have been black holes which were smaller than that, which have completely evaporated by now.
Okay, but how can we, you said that they can be as small as an electron, but we cannot see naked eye electron, and we have to use very specific instrument to grasp and to see objects that are this small. But sometimes we struggle to see gigantic objects which are out there in the universe. But then, how do we see these primordial black holes? At least, what are some techniques which can be deployed to detect these primordial black holes?
Primordial black holes, they are still a relatively new area of study. When I say new, I don't mean that studies on them have started lately. It's just that we know very little about them. So, in the domain of theory, they primarily come in the area of studying the early universe. When we talk about how the inflation must have happened, how the universe must have progressed from from the moment of the Big Bang till about 1 second after the Big Bang. Uh, what one would imagine is that, okay, the Big Bang happened, and uniformly everything started spreading out. And that's when we started getting matter. It eventually started forming stars, and that's how we started getting the entire astrophysical spectra. But the very existence of these primordial black holes, they that uh, goes to prove that, you know what, there must have been something which allowed for matter to get compressed into these little areas, into these very small pockets, and create these black holes. So uh, that is usually the domain in which primordial black holes find most of their study. Of course, there are theories which say that primordial black holes may be dark matter, and so all the dark matter detection techniques, uh, some of them can be employed to study about these. However, uh, the most important thing that people, that at least I have seen people work around, is the existence of primordial black holes. What can it tell us about the early universe? So there are different models in which people assume inflation to happen, the inflation process to have happened, and the fact that black holes, these primordial black holes, do exist. What can it tell us about those areas? Apart from that, of course, there are general methodologies in which we detect black holes. Most commonly, we have the gravitational waves that we usually see. So, uh, in a couple of years ago, we were talking about the LIGO experiment and the LIGO setup, in which they claim to have found out, detected gravitational waves. So there are the methods to detect black holes in that manner. The heavier ones specifically, that's so you detect them based on their gravitational effects.
Okay, so hopefully we will see major contribution from gravitational wave astronomy, which yeah, has been let's say has been launched pretty recently, I would say. And as you said, we had a major breakthrough for the first detection of gravitational wave. But as a very last question, tell us, what does it mean to have detected a gravitational wave from a black hole? What is the implication? Why do we want to be excited about that? Because we do see signals from many other objects in the universe. Why do we have to be excited about this detection of gravitational wave?
There are a couple of reasons. Like, first and foremost, the fact that there's a gravitational wave that we are detecting from a black hole actually proves in experiment that black holes do exist. Now, there have been people who have claimed that, you know what, in spite of whatever these theories predict, there is no such thing as a black hole. And those theories themselves do have a lot of weightage to them. But the fact that there is a gravitational wave which has been detected because of these black holes, and this predates the black hole image, which came out in 2018. The gravitational wave detection happened in 2015. So first and foremost, it tells us that black holes do exist. Secondly, they tell us about the mass of the black hole, the temperature of the black hole, and what sort of dynamics happen around the black hole. So, do black holes collide? What happens when black holes collide? What are the effects on the local space-time of black holes colliding? Uh, all of those ideas, all of those previously hypothesized concepts, they to some extent gain verification when we observe gravitational waves in an experimental setup. So that is one of the most important, aspects of gravitational wave detections that came up with the LIGO setup.
Okay. Anything else that we want to be excited about gravitational waves?
I think the fact that we know that gravitational waves have been detected, and that too with some one of the most basic concepts. When we study about interference in wave mechanics, right? That's one of the first things that you start to learn about that. The entire LIGO setup essentially uses a simple technique like that to describe, to prove the existence of these gravitational waves. And once you see something like that, you do get a lot more hopeful about the studies and the potential of utilizing black holes, if so, in uh, say the near or the far future, as sources of energy, as sources of other aspects. In fact, in science fiction, you would also find black holes to be gateways to other universes and all of that. So this detection can act as a small step towards getting into those theories, finding out how valid or invalid they may be. Uh, I think it is the first step onto deeper black hole detection, black hole physics.
Yeah. So we definitely hope that this, as you said, this is just the beginning of a gravitational wave astronomy, which hopefully can lead us to further and more, let's say, enlightening insights on black holes, these exotic objects which we know a lot, but I think also at the same time we don't know much about. There is much more to be unraveled from these objects. So yeah, I think the future is very exciting with regards to this topic. Okay, so yeah, I will. I thank you for your time. I will leave you. I think we can wrap it up here. And so thank you very much, Shreesh, for your time, and also
Thank you
for
for
your.
having me.
No, it was absolutely my pleasure. It is always great to be taught about some exciting topics like this one, like a black hole, especially. And so yeah, this was the fourth episode of Math and Beyond. And yeah, thanks for whoever who listened to this conversation. And I will see you in a later episode.